Hi, so we are back after almost a month of not putting out anything to the playlist. But anyways, what we discussed last time was ARC. We were talking about the adaptive replacement cache uh, and how that particular algorithm gives you a parameter P, which decides that uh, do you want to favor recency or do you want to favor frequency. So that particular algorithm gives you some sense of both recency and frequency for the pages. And we saw that how good algorithms try to balance between the two. So we went over the lookup protocol for Arc, that you have a ghost list and you have two lists. You have a recency list, you have a frequency list, and then you maintain special other two lists, which are the ghost list for the frequency list and the ghost list for the recency list. And then according to where you are experiencing cache misses, you tweak your parameter P to favor one of the particular parameter, like either you favor recency or you favor frequency. So we'll discuss some optimization that you can do to your bug pool, so that these are like good to know optimizations. Not all of the, like, various systems do different things, but these are like some basic approaches that you can take while you're building a database system. So one optimization would be that you could have special buffer pools for special queries. So, if you remember that we talked about something known as a sequential flooding, that when a query comes in and let's say a select statement comes in and it is going to scan a whole table which has 100 pages, let's say. So what that will end up doing is it will end up polluting your main buffer pool. So you are reading in 100 pages and you might be swapping out useful pages that might be hot, and you might swap those out in just to cater to that one select query. So what you can do, you can have special buffers for such queries. So in Postgres, you have something known as a circular ring buffer. So what you can think of it is like as you can think of this particular buffer pool like a array of memory, which is just laid out as a circle. If I divide these slots, so what I'll do is the iterator that will be reading from the disk will keep putting pages into the empty slots, and then it will move forward. Oops. Yeah. Then it will move forward to the next, fill it up, move to the next, fill it up, move to the next. And eventually I will touch the last page here, and then I don't have to do any computation, but just a modulus operation on the memory address. I do a modulus operation and I jump back to the page, the very first slot, and then I start filling. So assume that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 slots. So the iterator that would be reading from the disk would keep the very first page in the first slot, and then it will go around and fill 9 pages. After that, what it will do is it will jump back to the very first slot and fill the 10th page there. And then it will continue and fill these up to 19, 19, I guess, 10, 11, 12, 13, 14, 15, 16, 17, 18, 18. Fill these up to 18 pages. So what you are preventing is you are preventing your main buffer pool from being polluted by these unnecessary pages which might not be used in the future. So this is a good optimization that you can do to your buffer pool. Okay, what is next? We have something known as priority hints. What are priority hints? So you might give hints to your algorithm that these particular pages are important and don't swap them out. Like, you can swap them out, but you might not want to. So like if you can just avoid as much, like avoid of swapping these pages out. So if I was building a system that used a B tree, what I would do, I would assign the very high priority to the very first node of a B tree. So let's say I'm running MySQL. MySQL is a tree-based storage engine, and in order to traverse a particular table, you always go through the root. So the root page will be very hot. So what you'll do is each time a query comes in, assume you don't have indexes. Every time a query comes in, you hit the root page and then you decide based on the child pointers that way you want to go left or do you want to go to the right. So you can assign priorities to the pages. So the root page will have the highest priority. Why? Because it every query will enter through the root. I hope you're getting what I'm saying. But every query will enter through the root, and then you can have decreasing priority levels for different pages. The children being the least, because each query might need some different data. So, uh, how can I explain this better? We'll get to B trees. You might understand better when we discuss about B trees, but yeah, that's what priority hints are. You mark some pages as important, and you tell your algorithm to try and not to swap them out. And this is a good optimization that you can do actually. So, I don't understand. Okay, so there's an example. Let's say this query shows up. I'm inserting into the table and I'm inserting ID plus plus. So what I'll do is I have insert query which is inserting IDs, on an incremental basis. So the minimum ID would be on the leftmost page and the maximum ID would be on the rightmost page. So when I try to insert the query, first I need to do a lookup that which page deserves this key, which page I actually need to put it in. So obviously I will access the root, then I will compare that what is my root actually. My root is nothing but it is a array of slots and data. Sorry, not data actually, and child pointers. So we'll talk about B trees and how data is laid out. But usually the B tree nodes are slotted pages. So the slotted pages, you had the slot array in the start, and then you have the data that is getting appended from the end of the page, and then you maintain those pointers internally in the page to make the slot pointers point to the actual data. So a page can contain data, but a page can also contain pointers to other pages. So let's say to talk about the root, this particular root page has a slot array of keys, and you might be pointing to some data segment in the page, and that particular data segment might hold pointers to the children that if you want to go to the left or the right. But we'll talk about B trees and how they are laid out. But see, whenever we run this insert query, we'll always be accessing the root. So we need to give the highest priority to the root, that you don't need to swap this out. If you can, like if you can, then try and not to swap this out, because every query will enter through the root and then it will go scanning the tree, the children underneath it. So there's a query too, which wants to do a select statement, and let's say it's looking for some ID. So this particular statement will also enter through the root. So we need the root to be in memory, to be very, because it is a hot entry point. We need to keep it in memory. Okay, so that is with priority hints. Then we're talking about dirty pages, but I can't remember what I studied in the dirty pages. If a page is about food is not dirty, then the page. Okay, so dirty pages are nothing. This slide discussion is mostly about what policy you're going to choose to write dirty pages back out to the disk. So let's say a page is not dirty, then it is easy that it's not dirty. You can throw that particular page out. It is the identical copy that is lying on the disk. So you can throw the in-memory copy anytime you can. And if a page is dirty, then things get complicated. Then you need to decide that do you want to uh, implement a force steal policy, or you want to do a no force steal, no steal policy. So we'll talk about these policies in the upcoming lectures. So what happens is there are four slots actually. So there are two parameters, force, sorry, steal and force. And and there is no steal and no force. Sorry for my bad writing, but okay. So you can combine these four and you can fill these four slots. So what you can do is you can do steal with force or you can do steal with no force. So that is steal pairs up with force and no force, and then you create two different policies. Or you can do no steal and force, or you can do no steal and no force. So what I'm talking about is that assume that a page has been touched by a query. So a query is running, it initiates a transaction and it tells the transaction to bring in pages and it touches the pages. It does some write operations. It let's say it garbage collects and it just modifies the pages. Now your background writer, when you're doing commits and you're actually trying to commit, it depends on how you implement the system that do you want to write that particular page right now, or do you want to defer it? Do you want to defer the write to the to a particular, like you might want to do the write at some point in time, but not right now. Or you might want to force that yes, you need to write this particular page out before I give the response back to the user that yes, your changes have been committed. So we'll talk about these policies again, but your database management system's performance heavily depends on like minute things that you configure. So any uh, any choices that you make to what policies you implement will decide that how your database system performs in the long run. So background writing. This is what we were talking about in this dirty in this dirty pages wala topic. What we discussed was that when you dirty a page, you need to decide that when you're committing a transaction, you write that particular page out to the disk right now with the commit, or do you defer it to a particular future? But then you also have to see that if your system crashes and you come back up, then you also need to some way to figure out that these changes were not applied to the disk and I need to apply them back because I have given the response back to the user that yes, your commit has successfully executed. So which brings us to the next topic, background writing. So what is the background writing? Background writing is your pages are lying in the buffer pool and you have some different thread or a process which is reading pages from this buffer pool and writing them back out to the disk. Uh, why can't you do it sequentially? Because you can do it sequentially also that when a transaction finishes, you write those dirty pages out to the disk, but that is not very scalable because then at every commit you will be just figuring out that what is the latest version of this page that I want to write it out to the disk. So back in the background writing, you can figure out that particular logic that what I need to write out to the disk background without any giving any downtime to the user that yes, I'm doing some background writing at this particular point. So what this slide says is when a dirty page is safely flushed, the DBMS either evicts the page or resets its dirty flag. So when a page is actually written out by the background writer, so you can mark it as clean or you can throw that page out because you don't need it anymore, right? And maybe the transaction that was touching the page is done. Yeah, so you need to be careful that the system does not write dirty pages before the logs are written. What logs we are talking about here? We're talking about the wall, like the write ahead log, which stores that what changes were made. But we'll talk about that also. So there's some observation. OS hardware tries to maximize disk bandwidth by reordering batching IO requests, but they do not know which IO requests are more important than others. Deadline FIFO scheduler. Yeah, so this is a basic observation that they have presented that when you're writing things out to the disk, the disk controller, which is actually doing the work of writing the bytes, it just sees that all requests are equal priority. It does not differentiate that, yes, this is coming from a database management system, so I will give priority to this, but it just uh, serves them impartially. And it might also reorder things or batch things together. Like if you are writing to, let's talk about SSDs. So what you have in SSDs is you have a block, and within that block you have a page. So this particular page is different from what we are talking about, the DBMS pages. So those pages, the DBMS pages, are logical structures in our head. They are physical pages, but they are also uh, a way for us to think about database systems as files on disk. But okay, so what I was talking about was, yes, so when you issue bunch of writes to the disk, and let's say you're writing two blocks of memory that are close by, and you have another request which is writing a block that is far away. So what the disk controller will do, it might batch your these two writes, the writes that are lying close, in one particular write. Why? Because that is efficient for the controller. It will just have to do one write, and it can write out the both the packets. Uh, so yeah, to you as a operating system, it might be totally alluded to you that we are doing some reordering down in the disk controller. But yeah, controllers might do their own things beneath the hood.